I hope I'm audible. Good evening, everyone. This is the fifth live discussion session on the course Soil Mechanics Geotechnical Engineering 1. Uh, Today's topic of discussion will be Boussinesq theory and vertical stress distribution. So, Boussinesq theory is basically with respect to the stress distribution in soils. So this session obviously has some uh, many numericals along with multiple choice questions. I'll straight away go to the PPT and start discussing as usual. Yes. So I think the PPT is visible right now. The slides, yes. Okay. So like the previous sessions, this session has a set of questions containing multiple choice questions. It might contain true or false, and along with some numericals. I'll first dictate the questions and then I'll give you some time to solve them. After that, I will start discussing the solutions with the relevant explanations behind them. Okay. So this is the fifth live discussion session. The topic is Boussinesq theory and vertical stress distribution. I'll now start with the dictating the questions. Okay. The first question is, according to Boussinesq theory, the soil mass is. According to Boussinesq theory, the soil mass is. Your options are homogeneous and isotropic, homogeneous and anisotropic, heterogeneous and isotropic, or heterogeneous and anisotropic. You have to mention what does Boussinesq theory assumes about the properties of the soil. Does it assume the soil to be homogeneous or heterogeneous, or does it assume the soil to be isotropic or anisotropic? I'll repeat the question. According to Boussinesq theory, the soil mass is homogeneous and isotropic, homogeneous and anisotropic, heterogeneous and isotropic, or heterogeneous and anisotropic. Okay, I'll go to the next question. At constant R, that is, if R equals to 1 unit, the vertical stress is maximum at Z equal to, Z is the depth from the depth from the point of action of the load below the soil. Okay. So when the R is constant, R is equals to 1 unit, R is the radial distance, is 1 unit. At what depth shall we get the maximum vertical stress as per the Boussinesq theory? Okay. Your options are 1.225, 0.1225, 2.124 or 1.625? I'll repeat the question. At constant r is the radial distance, that is r equals to 1 unit. The vertical stress is maximum at z equal to, z being the depth. The options are 1.225, 0.1225, 2.124 or 1.625. Okay. Next question. Yes. At zero radial distance, the value of Boussinesq influence factor is. At zero radial distance, the value of Boussinesq influence factor is. The options are 0.647, 0.478, 0.888 or 0.239. That means when the radial distance r equal to 0, what is the value of the Boussinesq influence factor Kb? I'll repeat the question. At zero radial distance, the value of Boussinesq influence factor is 0.647, 0.478, 0.888 or 0.239. Okay, I'll go to the next question. Yes. A circular area of 7.5 meter in diameter on the ground surface carries a uniformly distributed load 3 kilonewton per meter square. Find the intensity of vertical pressure below the center of the loaded area at a depth of 6 meter below the ground surface. I'll repeat the question. A circular area of 7.5 meter in diameter on the ground surface carries a uniformly distributed load 3 kilonewton per meter square. Find the intensity of vertical pressure below the center of the loaded area at a depth of 6 meter below the ground surface. Okay, so here a circular area, the diameter has been given, the UDL load has been given, and it would to find out at a depth of 6 meter below the center of the ground surface, find the intensity of vertical pressure. Okay, next question. A circular area is loaded with a uniform load intensity of 100 kilonewton per meter square at ground surface. Calculate the vertical pressure at a point P so situated on the vertical line through the center of the loaded area that the area subtends an angle 90 degree at P. I'll repeat the question once. A circular area is loaded with a uniform load intensity of 100 kilonewton per meter square at ground surface. Calculate the vertical pressure at a point P so situated on the vertical line through the center of the loaded area that the area subtends an angle 90 degree at P. Okay, I'll go to the next question. Yes. A concentrated load of 200 kilonewton acts at the ground surface. Find the intensity of vertical pressure at a depth of 10 meter below the ground surface and situated at the axis of loading. What will be the vertical pressure at a depth of 5 meter and a distance of 2 meter from the axis of loading? So there are two scenarios in which you have to find out the intensity of vertical pressure. I'll repeat the question. A concentrated load of 200 kilonewton acts at the ground surface. Find the intensity of vertical pressure at a depth of 10 meter below the ground surface and situated at the axis of loading. What will be the vertical pressure at a depth of 5 meter and a distance of 2 meter from the axis of loading? I hope the question was clear. I will go to the next question now. So this chapter, this live session, discussion session is mainly composed of numericals and some multiple choice questions and others. Okay, sorry. Yes, sorry. Just a moment. Yes, so the next question was uniform intensity of loading at the foundation level of a building 10 meter in width and of infinite length is 100 kilonewton per meter square. Calculate the vertical pressure under the center line of the footing at a depth of 10 meter. So here we have been given a line loading of infinite length. The width is 10 meter and the loading intensity is 100 kilonewton per meter square. To find out the vertical pressure under the center line of the footing, center line of the width of the footing in a depth of 10 meter below the point of action of the load. I'll repeat the question. Uniform intensity of loading at the foundation level of a building 10 meter in width and of infinite length is 100 kilonewton per meter square. Calculate the vertical pressure under the center line of the footing at a depth of 10 meter. Okay. I'll go to the next question. Yes. A point load of 100 kilonewton acts on the ground surface. Find the maximum vertical pressure on a vertical plane at a distance of 2 meter from the loading axis. I'll repeat the question. A point load of 100 kilonewton acts on the ground surface. Find the maximum vertical pressure on a vertical plane at a distance of 2 meter from the loading axis. Okay. Next question. A concentrated load of 50 kilonewton acts vertically at a point on the ground surface. Compute the ratio of vertical stresses at a depth of 3 meter and 5 meter vertically below the point of application of load. I'll repeat the question. A concentrated load of 50 kilonewton acts vertically at a point on the ground surface. Compute the ratio of vertical stresses at depths of 3 meter and 5 meter vertically below the point of application of load. In case you haven't noticed, this question has not asked to find out the stresses, but you have been asked to find out the ratio of the vertical stresses at two different depths vertically below the point of application of load. I hope the question was clear. I'll go to the next question. Yes. A rectangular area of 2 by 4 meter carries a UDL, that is uniformly distributed load, of 8 ton per meter square on the ground surface. Find the vertical pressure at 5 meter below the center and corner of the loading area. I'll repeat the question. A rectangular area of 2 by 4 meter, that is 2 meter by 4 meter, carries a uniformly distributed load of 8 ton per meter square on the ground surface. Find the vertical pressure at 5 meter below the center and corner of the loading area. So you have to find out two answers. One, the vertical pressure at 5 meter below the center, and the next one at the corner of the loading area at the same depth. Okay. Next question. Yes. The vertical stress at some depth below the corner of a 1 meter by 1.5 meter rectangular footing due to a certain load intensity is 100 kilonewton per meter square. What will be the vertical stress in kilonewton per meter square below the center of a 2 meter by 3 meter rectangular footing at the same depth and same loading intensity? Here 100 kilonewton per meter square, this is the vertical stress and not the load intensity. Due to a certain load intensity, the vertical stress has been estimated to be 100. I'll repeat the question. The vertical stress at some depth below the corner of a 1 meter by 1.5 meter rectangular footing due to a certain load intensity is 100 kilonewton per meter square, what will be the vertical stress in kilonewton per meter square below the center of a 2 meter by 3 meter rectangular footing at the same depth and same loading intensity? Okay, I hope the question was clear. I'll go to the next question. Yes. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is. I repeat the question. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is. Your options are 1.22, 0.86, 0 or 1.62. I'll repeat the question. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is. The options are 1.22, 0.86, 0 or 1.62. Okay. Next question. This is an MCQ. Very easy question actually. The Newmark chart is based on. The Newmark chart is based on. Your options are Boussinesq theory, Westergaard's theory, equivalent load method, or none of these. I'll repeat the question. Newmark's chart is based on Boussinesq theory, Westergaard's theory, equivalent load method, or none of these. Next question. Yes. So in this question, draw the diagram very carefully or take a screenshot, whatever you feel is okay. Now you can see here we have the type of settlement and the type of pressure distribution which is arising from a particular foundation and a particular type of soil. Now from the settlement and the pressure distribution, you have to comment over here what is the type of foundation and soil present in this scenario. Comment on the type of foundation and soil from the given diagram. Comment on the type of foundation and soil from the given diagram. You have to comment on the type of foundation and soil from the given settlement and pressure distribution. Okay. I hope the question was clear. Next question. In the construction of the Newmark's chart, if the number of annular area selected is 10 and each annular area is divided into 10 sectors, the value of the influence factor for the chart is, I repeat, in the construction of the Newmark's chart, if the number of annular areas selected is 10 and each annular area is divided into 10 sectors, the value of the influence factor for the chart is, your options are 0.005, 0.05, 0.01, 0.001. The influence factor has a formula based on the number of annular areas and the number of sectors each area is divided into. You have to use that formula to find out the value of the influence factor. I'll repeat the question. In the construction of the Newmark's chart, if the number of annular areas selected is 10 and each annular area is divided into 10 sectors, the value of the influence factor for the chart is, the options are 0.005, 0.05, 0.01 or 0.001. Okay, I hope the question was clear. Next question. Yes. Originally, the number of sectors considered in the Newmark's influence chart is. So, in the previous question, actually, it was given the number of sectors, in each annular area. It was given in this question. But originally, what is the number of sectors each annular area is divided in the original Newmark's influence chart? Your options are 10, 12, 20 or 25. 10, 12, 20 or 25. I'll repeat the question. Originally, the number of sectors considered in the Newmark's influence chart is, options are 10, 12, 20 or 25. I'll go to the next question. Yes. Again, a similar question. Here also you have the settlement and the pressure distribution. Based on these two factors, you have to comment on the type of foundation and soil given from the given diagram. Okay, what is the type of foundation and type of soil? Okay, next question. Again a similar question. Here also the upper part in the dotted lines, it is the settlement, and the lower part showing the arrows, it is the type of pressure distribution. So based on this, you have to comment on the type of foundation and the type of soil. So in the previous diagram also you can see the arrows show the distribution of pressure, and above that it is the settlement. Here also same thing, the white portion below the ground is the settlement, and the arrows, it shows the pressure distribution. So you have to comment on the type of foundation and type of soil. Okay, next question. Yes. I have already started discussing the questions, so I'll be giving the solutions after a while. So you can write down the questions from this particular question. I'll just show you. This was the last question. What is the type of foundation and soil from the given diagram? Okay. And now this is the another question, a numerical. So a rectangular area 3 by 1 meter is uniformly loaded with loading intensity 100 kilonewton per meter square at the ground surface. Calculate the vertical pressure at a point 4 meter below one of its corners using the Newmark's influence chart if Na is 12. If Na is 12, what is Na? Na is the number of area units under the loaded area. Na is the number of area units under the loaded area. To find out the vertical pressure at a point 4 meter below one of the corners. I'll repeat the question. A rectangular area 3 by 1 meter is uniformly loaded with a load intensity of 100 kilonewton per meter square at the ground surface. Calculate the vertical pressure at a point 4 meter below one of its corners using the Newmark's influence chart if Na equals to 12. Okay. The last question is, comment on the type of foundation and soil from the given diagram. Here also the white portion, top white portion is the settlement of the foundation, and the lower portion showing the arrows is the pressure distribution. Is the pressure distribution. Okay. So from this particular uh, settlement and pressure distribution, you have to comment on what kind of foundation is this and what kind of soil is this. Okay, please draw the diagram or take a screenshot of it, whatever is comfortable for you. So I have given 20 questions over here. Each questions, there are many numericals, so you take time to solve them, and I'll be again starting the class at 7 o'clock in the same class. Those who have joined, stay in the meeting, solve the questions. Okay. Yes. So stay in the meeting, solve the questions. At 7 o'clock, I'll start discussing the solutions of all the questions. Okay.
Hi, sir. Hello.
Okay, so I hope I'm audible and the PPT is visible. So I'll now start with the discussion of the solutions one by one. If you have solved, I'll ask you. You can either tell me the answer or write in the chat box, whatever is comfortable with you. Okay. So the first question was, Yes. According to Boussinesq theory, the soil mass is. What is the answer? According to Boussinesq theory, the soil mass is. Any answer? Okay, so in Boussinesq theory, the soil mass is considered to be homogeneous, because if the soil is considered to be heterogeneous, then the properties of the various layers of the soil with various compositions have to be taken into consideration. That will be a tedious job. Okay, heterogeneous means the composition is different at different places. And what is isotropic? Isotropic means the properties are same in every location from one particular point. The properties are same in every location from one particular point. So for the case of simplicity and of the entire theory and the corresponding equations, in the Boussinesq theory, it is assumed that the soil mass is homogeneous and isotropic. The soil mass is homogeneous and isotropic. Okay. So according to Boussinesq theory, the soil mass is homogeneous and isotropic. Next question. Yes. At constant r, that is the radial distance equals to 1 unit, the vertical stress is maximum at z depth equal to. Any answer? Okay. So I'll first draw the diagram here. Using the formula only, it has been found out. I'll just give the concept. So if this is the load acting over here at this point, okay, if this is the radial distance r, this is r, so this is the point where I'm considering. So at this radial distance, first the load is remaining constant, it increases gradually, at a certain point it becomes maximum, and then it again follows the same path. So this point where it is the load is maximum, this is the vertical stress, sigma z. This depth z is equal to 1.255. You can follow any standard textbooks of soil mechanics, you will get the derivation the same. Okay, so at this depth, that is 1.225, sorry, 1.225, the vertical stress is maximum when r equals to 1. So at this point r actually equals to 1, then only will be getting the maximum stress at z equals to this. So this is sigma z, and this is what? This is sigma z max. Sigma z max. Okay. The value of the depth at which maximum vertical stress is obtained at r equals to 1 is 1.225. I hope it was clear. I'll go to the next question. Yes. At 0 radial distance, the value of Boussinesq influence factor is. Boussinesq influence factor Kb, the formula is 3 by 2 pi into 1 divided by 1 plus r by z. R is the radial distance, that is the depth, whole square, whole to the power 5 by 2, whole to the power 5 by 2. So now at 0 radial distance, it means that value of r equal to 0. The value of r equal to 0. This whole thing becomes 0, this whole thing becomes 1. The value of kb, it reduces to 3 by 2 pi. 3 by 2 pi. 3 divided by 2 into pi. It is almost equal to 0.478. Almost equal to, yes, 0.478. So in this case, you just have to remember the formula of the Boussinesq influence factor. The formula of the Boussinesq influence factor, that is Kb equals to 3 by 2 pi into 1 by 1 plus r by z whole square whole to the power 5 by 2, and r equal to 0. So the value of the influence factor reduces to 3 by 2 pi, which gives us a value of 0.478. Okay. Okay, next question. Yes. A circular area of 7.5 meter in diameter. Okay, so first of all, we will draw the geometry of the loading. So this is the, suppose this is the cross section, and at a depth of 6 meter below the ground surface. This depth is 6 meter. So this is 7.5 diameter. The radius will be how much? Radius will be 3.75. 3.75 meter. And in this diagram, in this geometry, this is 90 degree. So the value of this angle, if you solve this using simple trigonometry, the value of this angle you will be getting as, I think, 32 degree. 32 degree. Okay. Now this question you can solve using two formulas. The first formula is sigma z, that is the vertical stress, equals to q, that is the loading, intensity of loading, into 1 minus, within bracket, 1 by 1 plus a by z whole square whole to the power this thing, this part whole to the power 3 by 2, then the bracket. Here a is the radius, which is equal to 3.75, and z is the depth, which is equal to 6 meter. Now if you solve this, you will find out a is the radius, which is 3.75 divided by 6 whole square plus 1 divided by answer whole to the power 1.5, 1 minus answer into q. What is the value of q? Value of q is 3. Yes, you will find the answer to be approximately 1.17 kilonewton per meter square. Okay. Now if you don't want to use this formula, there is another formula for this circular loading or loading in a circular area. The formula goes sigma z equals to q loading into 1 minus cos cube theta. 1 minus cos cube theta. Notice theta is this angle subtended at the center and half of it, half of the angle subtended at the center. So if you do this cos 32, then cube 1 minus answer into 3. Yes, again you will get a value of around same thing, 1.17 kilonewton per meter square. So you can use any of the two formulas in this question to find out the intensity of vertical pressure below the center of the loaded area at a depth of 6 meters below the ground surface. Okay, I hope the sum was clear. Go to the next question. Yes. A circular area is loaded with a uniform intensity of, same question again, vertical line through center of the load. So it is the vertical line through center of the load at a point P such that the angle at point P, the angle subtended at point P is 90 degree. The angle at point P is 90 degree. Uniform load, that is the value of Q, equals to 100 Newton per meter square. So if the angle at point P, this is the point P, this is the circular loading with the UDL. Okay, this is the point P. What is the half of the angle? It is 45 degree, which is equal to theta. So using the formula in the previous question, the second formula, that is sigma z equals to how much? Q into 1 minus cos cube theta. Q into 1 minus cos cube theta. Okay, Q is 100, cos theta is 45, cos 45 whole cube, 1 minus answer into 100. 64.64. Yes, 64.64 kilonewton per meter square. So here the diameter is not given, depth is not given, so A and Z you cannot find out. You have to go with the second formula, that is find out the angle theta, that is half of the angle subtended at that particular point, and then use the formula sigma z equals to Q into 1 minus cos cube theta and get the value of the vertical pressure at the point P. Okay. I hope it was clear. Next question. Yes, a concentrated load 200 kilonewton acts as the ground surface. So this concentrated load 200 kilonewton, this is definitely the load which we use in the Boussinesq theory. Not this. This is the value of Q. This is the value of Q. Now this question has two parts. The first part, depth is 10 meter. Z equals to 10. R equals to situated at the axis of loading. So R equals to 0. In the second part, Z equals to 5. R equals to how much? Distance of 2 meter from the axis of loading. R equals to 2. R equals to 2. So here we have formula. The main formula is, that is sigma z equals to 3q divided by 2 pi z square 1 divided by 1 plus r by z whole square whole to the power 5 by 2. Here the value of r is 2, value of z is 5, the value of q is 200 kilonewton, again z over is 5, you use this value, and over here in the first instance, what will happen is the value of r equal to 0. Value of r equal to 0, so this part becomes 0. Okay, so this entire part becomes 1. So here you can use the simplified formula sigma z equals to 3q divided by 2 pi z square. Okay, use this formula and you will find out that I think in the first instance, I'll just calculate once again. I think in the first instance 600. 2 into pi into z is 10. Yes, it is 0.955. 0.955. Okay, 0.955. The value is in the unit is kilonewton per meter square. And the second instance, R is 2 by 5 whole square, 1 plus answer, 1 divided by answer, whole to the power 2.5 into 3 into 200, yes, divided by 2 pi into, there is pi 25. Yes, the value is 2.64. 2.64. Again, the unit is kilonewton per meter square. Okay. So, two different cases. You have to use two different scenarios. Same formula, just bending it a bit and finding out the solution. Okay. Next question. This is a question of line loading. This is a question of line loading. Okay. So when there is a line load of infinite length, we consider the width only over here. So here this is the width of the load and it is infinite length towards the plane of the screen. So this is the width of this and the center line is this, depth of 10. So this depth is 10. I'll again join this to make it a triangle. Yes, this is depth is 10. Okay, this is the value of q. I'll not write it here. This is q, and then 10 meter in width, that is this is half is 5 meter, this is 5 meter. Now using simple trigonometry you can find out that this angle is almost equals to 26.57. yes, 26.57 degree. Now for the line load we have the formula, okay, sigma z equals to q by pi into theta plus sine theta. Theta plus sine theta. Now here what is theta? For the line load of infinite length, theta is the angle subtended at the center. That is the entire angle. That is double of this. So this is equals to theta by 2. Hence theta will be equals to twice of this. So it will be how much? 53, approximately 53.14 degree. Now this degree value I can place in the sine theta part. Now what about the theta part? You have to convert this degree into radians. So theta in terms of radians is 0.927. Okay, I'll just solve it once again. Yes, so theta, to convert it into radians, you have to multiply the angle with pi and divide the same by 180. So 53.14 into pi divided by 180. You get the value of 0.927. Okay. Now put the value q equals to 100 divided by pi in bracket. Theta, that is 0.927 into sine theta, that is sine of 53.14 degree. The value of this stress will be approximately equal to 54.98. 54.98 kilonewton per meter square. Okay, so this is the main formula of line load, and you have to take the angle theta as the entire angle subtended at the point of consideration. Okay, I hope the solution was clear. I go to the next one. Yes, a point load of 100 acts on the ground surface. Find the maximum vertical pressure on a vertical plane at a distance 2 meters from the loading axis. So in the I think second question, we have learned that when R equals to 1, the maximum stress was at Z equals to 1.225. So we'll write over here, when R equals to 1, okay, for sigma max Z equals to 1.225. Now again, when R equals to 2, distance of 2 meters from the loading axis, R equals to 2, when the radial distance is 2, that is, it has gone further away from the point of contact, from the point of application of the load, then for sigma max Z also will be twice the maximum. If the further it goes from the line of application the load, the deeper we obtain the value of the maximum vertical pressure. Okay, so Z equals to will be how much? Twice of the first value, that is 2.45. 2.45 meter is also meter. Okay, so here we have the value of the load, point load, that is Q. This is the value of Q. We have R, we have Z. Now putting everything in the formula, so sigma Z max, again Boussinesq theory, 3Q divided by 2 pi Z square 1 divided by 1 plus R by Z, this one whole square, whole to the power 5 by 2. Put everything in the formula, you get a value of approximately 2.22 kilonewton per meter square. Yes, 2.22. Okay, so I'll just repeat the solution here. What have I done? I have just found out the value of Z for the maximum vertical stress when R equals to 2. If at R equals to 1, the value of Z for sigma max is 1.225. Then for R equal to 2, it will be Z will be 2.45. It is the double of the first instance. Then we have got the value of Z, the value of R, we have the value of Q. Putting them in the formula for the Boussinesq theory, sigma max, sigma Z max equal to, we get the value of 2.22 kilonewton per meter square. Okay. Next question. Okay. A concentrated load of 50 kilonewton acts vertically at the point in the ground surface. Okay, so in this question we are asked to find out the ratio of the vertical stresses. The ratio of the vertical stresses. So we know sigma from the formula in the Boussinesq theory, sigma is indirectly proportional to the square of the depth, isn't it? In the formula you can see sigma max, below it is Z square at the denominator. So sigma directly proportional to Z square, 1 by Z square. So we can say that sigma 1 by sigma 2 will be how much? Ratio Z2 by Z1 whole square, isn't it? So vertical stress at a depth of 3 meters. So this is at depth of 3 meter. This is the depth of 5 meter. So Z1 will be how much? 3 Z2 will be how much? 5. So it is 25 by 9. The value is 2.78. Yes, 2.78. Okay. So the concept is the value of vertical stress is inversely proportional to the square of the depth. So sigma 1 by sigma 2 is equals to Z2 by Z1 whole square, and in this way we can find out the ratios of the vertical stresses without actually finding out the vertical stresses. Okay, I hope it was clear. Next question. Yes. So here we have a rectangular area and a UDL. Okay, we have to find out the vertical pressure. Now in this question what we'll do, we will convert the UDL to point load. How can we do that? So we have a rectangular area like this, 2 meter by 4 meter. Okay, so it has a uniformly distributed load. So total load, if we find out, it will be the UDL into the area. The UDL into the area. So Q equals to 8 ton per meter square. Then Q will be how much? What is the point load? It will be Q into area. Okay. What is area? Area is 2 into 4, that is equals to 8 meter square. The value of the point load will be 8 into 8, 64. 64 tons. Yes, 64 tons. Okay. Now another thing, we are asked to find out the vertical pressure 5 meter below the center and corner also. So in this rectangular area, if we draw this again in a magnified size, this is 2 and this is 4. Now this is the center and this is the corner. Okay, this is the corner. So 2, half of 2 is 1, half of 4 is 2. Then this distance from the center to the corner, because obviously the point load is acting at the center. So at the corner of this loading area, this will be R, and R will be equal to how much? Using the geometry of this, rectangle, Pythagoras theorem, it will be 1 square plus 2 square root over, isn't it? 1 square plus 2 square root over, it will be root over of 5. Will be root over of 5, isn't it? Is it clear? The value of the radial distance will be equal to root over of 5. Now in this formula, that is sigma z, again CQ divided by 2 pi z square 1 divided by 1 plus r by z whole square whole to the power 5 by 2. So at the center, obviously r will be equal to 0. At one place r equal to 0, putting r equal to 0 and z equals to 5. Z equals to 5, we'll get the first value, that is almost equals to 1.22. Sigma z at r equal to 0 is 1.22. Okay, in ton per meter square. Okay, now if r equals to root 5, then we'll get sigma z at root 5 equals to, putting r equals to root 5 in the same formula, we'll get a value of approximately 0.77. Yes, 0.77 ton per meter square. Please do this and verify the answers. There might be some discrepancies in the decimals part, so please solve it and verify the answers. Okay, so the first part, at the center r equal to 0, the answer is 1.22. The basic formula is 3q by 2 pi z square, And then the next part, r equals to root over of 5. The value of the vertical stress is 0.77 ton per meter square. Okay. I hope it was clear. Okay. Next question. The vertical stress at some depth below a corner of 1 meter by 1.5 meter. Okay. So this is 1 meter and this is 1.5 meter. This is a rectangle. Suppose. Okay. 1 meter and this is 1.5 meter. Vertical stress at the corner means at this point. Okay. At this point. At this point, the vertical stress is 100. It is 100. Okay. What will be the vertical stress in kilonewton per meter square below the center of a 2 meter by 3 meter rectangular footing? Okay. So now if we consider the present geometry and the next geometry, we can see that if we draw another line over here and if you draw another line over here, then make it another line means another 1 meter line and here another 1.5 meter line, and then make it a full rectangle. Make it a full rectangle. Then we'll see that this is actually a 2 meter by 3 meter rectangular footing which is asked right now. Okay. So in the first instant only this one particular block was considered, and due to this 1 meter by 1.5 meter block, the vertical stress at the corner at this point, okay, at this point was 100. Now if we consider this one, this particular rectangle, then again it is 1 meter by 1.5 meter. This will again exert a pressure of vertical stress of 100 kilonewton per meter square at the corner, that is at this point. Now again for this particular block, this will again exert a vertical stress of how much? 100 at the corner of its geometry, that is at the center of the entire rectangle, and again at last for this particular block also it is 1 meter by 1.5 meter rectangular footing, due to which a vertical stress of 100 kilonewton per meter square will be exerted at the corner of the footing, that is at the center of the entire block. So you can see that at each corner a value of sigma z equals to 100 for each block, isn't it? For each of the block, value of sigma z equals to 100 is being exerted. So in the next question we will have to find out the vertical stress below the center of a 2 meter by 3 meter rectangular footing. 2 meter by 3 meter rectangular footing. So this center means the corner of all these rectangles. So there are 4 rectangles. So this, the ultimate sigma z, suppose this point is P, sigma z at the point P will be 100 of each multiplied by 4 rectangles. 4 rectangles of 1 meter by 1.5 meter each are exerting a stress of 100. So the vertical stress below the center of this 2 meter by 3 meter rectangular footing will be 400. 400 and the unit will be kilonewton per meter square. Okay. I hope it was clear. I'll just repeat once. Each individual rectangular block of 1 meter by 1.5 meter is exerting a vertical stress of 100 kilonewton per meter square at the corner. So all the 4 blocks exerting the same pressure at corner, it means that exact intensity of pressure will be multiplied by 4 to find out the intensity of vertical stress at the center of the larger rectangular footing, 2 meter by 3 meter. Okay. I hope it was clear. I'll go to the Next question. Yes, next question is the intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load. So this is a tricky question actually. So if this is the load for Z is 4 meter at a point 4 meter directly below, this is the point P. Okay, then the value of R is equal to 0. So there will be sigma Z, but there won't be any radial shear stress. This tau radial shear stress will be 0 because R equal to 0. At the center there is only compressive force or compressive stress. There is no shear stress. Once we start moving from the center line towards one side or the other, then the value of R gradually increases and there is a radial shear stress. So when R equals to 0, because the point is directly below the 2 tons point load, then the intensity of radial shear stress is 0. The intensity of radial shear stress is 0. Okay. I hope it was clear. Next question. Yes. This is an easy question. The Newmark chart, where we divide the area into several annular areas and sectors. It is actually based on Boussinesq theory. Okay. Actually based on Boussinesq theory. Boussinesq theory has been modified and remade, and the Newmark chart has been based on the original Boussinesq theory. Okay. Next question. Yes. Here we have settlement and pressure. So in this case, we have to find out the type of settlement and the distribution of pressure to comment on the foundation type. Now we can see over here the settlement is uniform. This is the pressure distribution. In this pressure, the settlement is uniform, constant pressure. If the settlement is uniform, then that means it is a rigid footing, rigid foundation. Okay, rigid footing. Now you can see the pressure distribution. The pressure distribution is, as you can see, it is minimum at the center of the footing and maximum at the corner or the edges of the footing. This type of pressure distribution is generally found in cohesive soils. Okay, cohesive soils. So this is, you can tell the soil is cohesive soil, or you can say the soil is clay, whatever. I'll just name it as clay. The soil is clay. So rigid footing on clayey soil. Type of foundation is rigid and the soil is clay. Okay. Next question. In the construction of the Newmark chart, the number of annular areas selected for is 10 and each annular area is divided to 10 sectors. So influence factor basically is the total area divided by number of annual areas and number of sectors in each area. So if the total area is 1 or unity, then you will get the influence factor as area divided by number of annular areas, which is 10, divided by number of sectors in each area, it is 10. 1 by 100, that is 0.01. 0.01. So the value of influence factor is equal to the area divided by the number of annular areas and the number of sectors in each annular area. Okay. Now in the next question, it is similar thing. Originally the number of sectors considered in the Newmark influence chart. Here I have asked, that is the number of sectors is 10. What is the value of the influence factor? I have asked specifically if it is 10. Now in the original Newmark chart, the number of sectors is actually 20. Okay, for which the original influence factor, it becomes 1 divided by the number of annular areas is 10 and each annular area is divided into 20 sectors. So the influence factor becomes 1 by 200, that is, I think, 0.005. Yes. 0.005. Okay, but here I have asked only the number of sectors, it is 20. Okay, number of sectors in the original Newmark's influence chart is 20. Using this, the influence factor, the original influence factor for the Newmark's influence chart is 0.005. Okay, I hope it was clear. Next question. Yes. Again, we can see that here the settlement is uniform. Settlement is uniform. Okay. So this is again a case of rigid footing. Now in this case, the pressure, the contact pressure, we can see it is maximum at the center, minimum at the edges. This kind of pressure distribution is generally found in cohesionless soils, sandy soils. Okay, so I can say the type of soil, it can be sand. Rigid footing in a sandy soil, because the pressure distribution shows maximum pressure at the center of the footing, minimum at the corners or the edges, which is sand, and the settlement is uniform throughout, so the footing is actually a rigid footing. Okay. Next question. Here we can see that unlike the previous two cases, the settlement is not uniform, however, the pressure is constant. The pressure is constant. When the pressure is constant and the settlement is variable, the footing is flexible footing. Flexible footing. Okay, because the pressure distribution is constant, but the settlement is variable. It is flexible footing. Now, based on this settlement, we can see that the settlement is maximum at the center. Maximum at the center, minimum at the edges. So this type of settlement is generally found in cohesive soils or clayey soils. So I'll write over here clay. So this is a type of flexible footing in a clayey soil. Flexible footing in a clayey soil. Okay. Next question. Rectangular area of 3 by 1 meter with load intensity of 100, vertical pressure at a point 4 meter, below one of its corners using the Newmark's influence chart. Okay, so in this question, we have vertical pressure at a point 4 meter below one of its corners. Okay, so we can find out the geometry and do it, but we are told to use the Newmark's influence chart. Where NA, what is NA? I have told you NA is the number of area units under the loaded area. So if we have NA given, we can directly use the value of sigma Z as Q into IF influence factor into number of the area units NA, where NA is 12, Q is 100 loading intensity, and IF, I have told you in the original Newmark's chart, IF means influence factor, entire area divided by the number of annular areas and the number of sectors in each area. It is 1 divided by 10 into 20, it gives us a value of 0.005. 0.005. So putting the value of all these variables, Q is 100, IF is 0.005 and NA is 12. We get a value of 6 kilonewton per meter square. 6 kilonewton per meter square. So the main advantage of using the Newmark's influence chart is if the value of NA, number of area units under the loaded area, is given, we don't have to find out the value of R and use with the Boussinesq equation, TDS equation. We can easily use the formula sigma Z equals to Q into IF NA. Q is the loading intensity, IF is the influence factor, and NA is the number of area units under the loaded area. We can directly find out the vertical stress. Okay. Okay. The last question. Yes. Comment on the type of foundation and soil. So here also we can see that the pressure distribution is uniform or constant and the settlement is variable. Okay. Again, it is a what? It is a flexible footing. It is a flexible footing. Uniform contact pressure, it is a flexible footing. Now, here the settlement, we can see that the settlement is minimum at the center and maximum at the edges of the pressure distribution. Settlement is minimum at the center, maximum at the edges. So in this case, this kind of soil is generally cohesion-less soils, or I can say it is a sandy soil. It is a sandy soil. Okay. So in this case, we can see the contact pressure of the soil and the footing. It is uniform, but the settlement is non-uniform. It is a flexible footing. In the settlement, the settlement is minimum at the center of footing and maximum at the corner of the edges. So this is an example of a cohesionless soils. Hence, I can say this is a sandy soil. Example of sandy soil. Okay. So this is a flexible footing in a sandy soil. Okay. Any questions? Any questions regarding the session? Okay. So thank you for attending the session. We'll again meet in the coming Monday with the next session at 6 p.m. Okay. Thank you.